Alright, next we're going to do motion in space. So starting new chapter 13.4, now we're going to talk about motion in space. And so we're going to talk about velocity and acceleration, in the three-dimensional coordinate system, so in space instead of on the plane. So suppose a particle moves through space so that its position vector at time t is r of t for small values of h, so that we have the vector r plus c r of t plus h minus r of t h for very small values of h approximates the direction of the particle moving along the curve r of t. Its magnitude measures the side of the displacement vector per unit time. So the velocity vector v of t at time t is defined by, so here's just the limit definition of the derivative, and so we get v of t is equal to r prime of t, just like it is in two-dimensional. Thus, the velocity vector is also the tangent vector and points in the direction of the tangent line. So velocity vector, tangent vector, same thing. And then the speed of the particle at time t is the magnitude of the velocity vector. So again, just like in Calc 1, Calc 2, the magnitude of our velocity is going to be the speed. But in this case, we say velocity vector. As in the case of one-dimensional motion, the acceleration of the particle is defined as the derivative of the velocity a of t, which is equal to the derivative of our velocity vector, which is the second derivative of our position vector. All right, so really, there's not anything that is new except for we're adding, an extra, component in this case, or variable, for our acceleration and velocity. So now, example 1, find the velocity, acceleration, and speed of a particle with the given position function. And so we're given the position function r of t, and we want to take the derivative and the second derivative to find velocity and acceleration. And then we'll also find speed as well. So rt is the vector 2 minus t and 4 square root of t. So this is a two-component vector. So really, there's not a lot that's different here, okay? Because, we have two components. We could say that's x, that's y. So let's go ahead and now, but this is like taking the derivative of parametric equations. So r prime of t is just going to be -1. And when we take the derivative of 4 square roots of t, we're going to get t, it's really t to the 1/2, so multiply, so that's 2t to the -1/2. All right, again, if you have questions about that, just, please let me know. And then the second derivative of t is just equal to 0, multiply again, so t to the -3/2. All right. And so there is our velocity vector and our acceleration vector. All right, so we found a velocity vector, acceleration vector, and now let's go ahead and find our speed. So it's just the absolute value of our velocity. And so we get the square root of -1 squared plus 2t to the -1/2 squared. And so we finish with -1 squared is just 1, plus 2 squared is 4, t to the -1/2 squared is going to be -1, t to the -1, so over t. And there's our velocity function. All right, sorry, that's our function for speed. All right, now we want to find all this at t equals 1. So at t equals 1, we have velocity of 1. We just plug in, so we get -1. Plug in 1, so -1. Square root of 1 is 1. 2 over 1 is just going to be 2. Acceleration, plug that in. Acceleration at 1, our x component is going to be 0. Our y component, plug it in. We're going to get, don't want to forget, I did forget my negative there. And so we get negative, let me go ahead and put this velocity vector there as well. All right, and so we get -1 for our acceleration vector. Alright, and now what we would be finished, but it now wants us to sketch this on a curve down. This isn't going to be too complicated. Again, if we were going to sketch something, I'll change my colors. We would say x is equal to 2 minus t. So we could say t is equal to 2 minus x, and we can say y is equal to 4 square roots of t, or we could say y is equal to 4 square root of 2 minus x. All right, now if we're going to actually, so I do that so I can draw what my graph is going to look like. Again, I'm not drawing a lot of straight lines today. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now what we're going to do is we're going to go ahead and I'm going to I'll just plot my equation in green. And so here we know that when x is 2, we're going to be a value of 0. When x is 1, we're going to be a value of 4. And, the next value that we would get would be, the next whole number we would try would be, looks like negative, let's see, 2, so negative 2. And that would give us 4, 8. So it would give us a value up here. So I'm just going to go ahead and connect everything that we have. All right. And what we want to do is just we want the value at 1 when t is equal to 1. And we just want to plot our velocity and acceleration vector. So our velocity vector, I'm going to go ahead and denote with that in orange. And so velocity vector, so at our point, we're going left 1 and up 2. Right, so this is not the best. Let me try to draw it a little bit better, because it should be on the outside. Alright, so again, it's not going to have to be perfect when you're drawing these, and I should have just done that in orange. And then our acceleration vector, I'm going to do that in blue. So 0, negative 1, so 0, negative 1. And there's the acceleration vector. And that's all you need to do for that. All right, the last thing is, in general, when we're doing vector integrals, it allows us to recover. We can find velocity and acceleration from known positions when we, when we know, a certain initial, when we know a velocity is known and a position is known, we can get back to the original position vector. And so again, that's really similar to finding back the original function in Calc 1 and Calc 2.